So now I'm putting on my hat as one of the co-leads of the Development of Intelligence mission with Laura Schulz. I'll give the first part and then hand it over to Laura. And I think you will see many resonant themes with all of the other talks, and it's really exciting to be sharing the stage with all of you guys and seeing all the ideas and their cross-fertilization. So here's our team. There's a couple of other faculty PI leads. Rebecca Sachs, Vikash Mansinga has contributed here, many great students and postdocs, as well as the CHS platform team, which you'll get to hear from under Melissa Klein-Struhl in the poster session. So I encourage you to check out several posters here. We'll highlight them. And there's also a lot of posters from language, so check those out to get some of the specifics in what you heard about before. Development of intelligence in Silicon Valley looks like this. It's all about the scaling laws. Scale data, scale compute, scale all the way. And we've seen, again, the great successes that can achieve and the great costs. But here's our North Star. Imagine if we could build a machine that grows into intelligence the way a person does, that starts like a baby and learns like a child, with an architecture and internal processing mechanisms that mirror the mechanisms and architecture inside the human brain that let us grow into intelligence. That would be, we think, both potentially a much more efficient, data efficient, cost efficient, energy efficient route to a machine learning system that really grows into all the things that a human adult can grow into, and most importantly and most deeply, a model of the origins of our own minds. To really illustrate how different this vision is, here's my sort of 3 take-home bullet points on the diametric opposite nature of the Silicon Valley scaling route, today's machine learning and today's AI, again, which with all the remarkable things that it's brought us, and the even more remarkable way that humans grow into intelligence. And you can just sort of put these into 3 key buckets, right? In the machine learning route, the whole point is that the learning mechanisms are dumb. Dumb is good in the sense that they are simple and scalable, and you can pour more compute and get something predictable out. But the system doesn't start off intelligent. It just starts off finding patterns in next token prediction. Intelligence, such as it exists in those systems, is an emergent property, the end result of learning. The result is that it can be quite successful, but it's also, as Jacob has said this very well, many people in AI have said, it can be jagged, sometimes superhuman in other ways, and crazily, confoundingly far less rational than humans in other ways. Hard to predict, especially when we're talking about anything that goes beyond the distribution of training. And lastly, really just building on the themes that you heard with Ev, in this view, you start off modeling patterns in language, and then at the end, various kinds of thinking sort of emerge, okay? If you get the right kind of data and you train it in the right kind of way. Other kinds of patterns of thinking maybe don't emerge, and again, hard to predict. But in humans, we start off intelligent from the beginning. There's something about the architecture of our mind, how we understand the world, and intelligent learning mechanisms. Those let us learn much more quickly, okay, from far less data. It's something to do with world models. So again, a theme you've seen throughout all the presentations, our minds and our brains are built to model the world from the start and to generalize based on those models rather than just patterns and data. Those models themselves learn and have to be responsive to data, but it's that model-based approach to generalizing beyond the data, just like the model-based versus model-free contrast you saw with Leslie and Nancy, that is so key to our intelligence. And thinking, in this view, is a thing that is present from the beginning. Even infants' brains, even non-human animals who don't have language and will never get language, they have a kind of intelligence, they have world models, they think as well. And it's really important that language, when it's learned, is built on and is enabled by that pre-existing thinking. That's how we can learn so much more quickly and so much more robustly. At the same time, having learned language, it then becomes a superpower for thinking and learning, unlocking many new kinds of thinking and learning abilities. Okay. So in trying to understand this from a developmental point of view, we've been guided by insights from the field of cognitive development, especially from our colleagues here, Laura and Rebecca, and their labs over the years, in terms of understanding both what's built in and how you might learn the rest, right? Built-in representations, basic kinds of world models for the physical and social world, algorithms for thinking, inference, and decision-making, but also various kinds of goals and motivations, okay? Not just seeking seeking pleasure and avoiding pain, but epistemic goals seeking to understand, and social goals seeking to be understood and connect with others. At the heart of all of these is some kind of basic notion of rationality. I'm not going to dwell on this, but I think you've seen it in many of the different pieces, that the architecture, the representations, and the goals are deployed fundamentally to make good guesses and good bets. Probabilistic inference, expected value decisions, plans that we have good reason to think, that's what it means to be rational, are going to do what we want. Okay. And then learning, in this view, you can think of it as something that happens all throughout the stage, but certainly sort of learning language is the hinge, but there's important learning that goes on even in infancy, before language. Then there's learning language, roughly from about 1.5 to age 3 or 4. And then there's all the kinds of learning you do after language that are enabled by the ways of learning from others and connecting with others, and not just people right in front of you, not just in your lifetime, but all the knowledge that's accumulated culturally across generations. So on the computational side, where my lab specializes, again, we're using these tools, the probabilistic programs, to capture really this whole learning arc here. I'll just say a little bit about what we've been doing in the first stage and then hand it over to Laura to talk about some of the later things that happen after language and even in the earliest stages of language acquisition. But just to highlight some of the things we've done over the last few years here, both in physical world models and social world models. The idea, for example, that we have, as Nancy talked about, some kind of physics engine in our brain that can simulate, at least on short timescales, and then take multiple samples of multiple possibilities of what could or is more or less likely to happen, has let us model some of the most classic examples of infant physical cognition, like the surprise that you might have, even if you're a young baby, when two objects go behind a screen and only one appears and the other one is gone. Or the surprise you might see when that screen there kind of goes back and goes through, apparently, an object that you thought was there. These can be modeled with some kind of probabilistic sample-based simulations. And in other displays like this, where we can parametrically vary, for example, how many objects there are of different kinds, what colors they are, where they are, when the screen is occluded, how long it takes before one appears. This is a way that people have studied quantitative graded predictions, graded surprise signals from infants, which can be predicted by the probability under one of these probabilistic physics-based world models. Even more interestingly is when you apply these to social cognition. So like the ability of even 1-year-old babies to see scenes like this and get a sense of which one agent is chasing another and one is fleeing another. Or that this agent here might really want to get to that blue object based on the fact that it's willing to jump over a high wall. Or even to this older baby here in the classic experiments of Warneken and Tomasello, the ability to see somebody doing an action you've never seen before, figure out what they're doing and how to help them. And these models also, going back to the AI side, have really set the new standard in benchmarks of physical and social common sense, like machine theory of mind. Okay, so now I'm going to hand it over to Laura to talk about some of the later phases and especially some of the really long arc of cognitive development. Because as much as we can model some of these rational kinds of inferences about physical world and social minds at early stages, it takes a surprisingly long time, as we've discovered, and there's really interesting development and computation that goes on there. But first, I'll just teaser for a poster, which we're not going to talk about, but some of the really cool work looking at the development of probabilistic programs. So go check out this work from Tracy Mills, Nicole Coates, and others at the poster session, where again you'll see that the ability to learn probabilistic models of symbolic structure in the world is something that adults have in remarkable ways, but again develops in really qualitative ways over the first years from 3, 4, 5, and check out their poster to see more of that. Okay, Laura.
Thank you so much, and it's a real pleasure to be here. So I'm going to talk about these later years here. And again, this mission is to understand how we start as babies and grow as children. And the vision here is a benevolent spiral where you are inspired by the computational models and the experiments that you design, but then the experiments you design may sometimes turn around to generate data that changes and informs the modeling approaches we've been taking. So I'm going going to show you two experiments that I think actually complete that spiral, or at least launch that spiral in some interesting new directions. One is on possibility and planning with 4-year-olds and older children, and the other is with very young children. So I'm going to start with possibility and planning. It's grounded first in the understanding that young children have an intuitive physics of the world that can represent how objects are going to fall, interact with obstacles, make predictions accordingly. But what we're going to ask here is, what can children do when they have to represent multiple mutually exclusive possibilities for the world? So imagine there's that orange ball there. It's going to drop. It's going to hit that obstacle. It's going to land in a bin, and your job is to make sure that doesn't happen. You can catch the ball using those blue cushions over there. So this is a participatory moment. If you need to catch that ball and you have 2 cushions, can you shout out what bins you're going to put those cushions in? 1 and 3. Excellent. You must be adults. And you are capable also of doing multiple simulations for this single event outcome, right? So we wanted to know, motivated by this, whether children could as well. So we're going to call these possibility trials, and we can compare them with a deterministic case where there is only one location that ball can land up. Right? So there's one ball and it's going to land in only one place, or there are 2 balls and they're each deterministically going to land in only a single location. So children are the participants get 3 trials of each type, and children are taught that they should stack the cushions if there's only one place the balls can land, and spread the cushions if there are 2 places the balls can land. And then the question is, what do they do on the critical possibility trials? And the answer, which was kind of stunning to me, maybe not so much to my co-author Brian Lee, who predicted things like this, is that children are startlingly bad at this. They are not representing multiple mutually exclusive possibilities for a single event. In fact, across all of these studies, the possibility trials pattern more closely with the 1-ball trials than with the 2-ball trials. They are tending to stack the cushions. This isn't because they like to gamble. They have to sit on their hands and have a 5-second timeout if they miss that ball, and they are not happy about it. In fact, we had crying children and had to terminate the study. So they want to catch the ball, and they are still missing the ball. This is true even when we first also teach them about possibility and teach them to spread the cushions. It is true even when we ask them, which way will the ball fall if it goes that way? Which way will the ball fall if it goes that way? And they still stack the cushion, even though they spread them when they're 2 deterministic possibilities. Okay, so this was striking, and again, somewhat of a violation of expectations, given that we know adults run multiple simulations for these events. So we ran a large-scale online replication with the simplest possible version of this task. This is only possible because of the kind of platform that has been supported by CBMM, by NSF, and really critically by the MIT Siegel Family Foundation, the Quest for Intelligence. And this platform enables us to collect data at scale from children online in automated testing. And it's now adopted by developmental labs across the country and actually around the world right now. Okay, so what do? It's exactly like this, but we thought, well, maybe the problem is kids have difficulty with the planning aspect. So we handed them the plans, and we just asked children to make a forced choice. Should you do this or that or this? And the answer is, children did exactly the same thing. 4-year-olds continued to favor the stacking option. And if you look at the developmental trajectory, there are 50 kids in each age bin. This is 250 kids from 4 to 8. All the way through 8, children's responses are not yet adult-like, right? So that is really stunning. Now, my analysis here is saying the kids are not good at this because compared to adults, they are not, right? But we can use the computational models to start asking, how does this ability emerge? What is going on? What changes? So if you look at individual data, and again, this is work with Brian and Vicente Vacano on the modeling. If you look at each individual child, this is a related experiment. You'll see it in the poster session later. What you'll see is patterns of behavior that look like this, which is to say this child is actually simulating multiple outcomes a lot of the time. Not as much as they should, which is 100% of the time, but a lot of the time. So they're better fit, by a multiple simulation model. As opposed to this child over here, who is not never simulating multiple outcomes, but extremely rarely, and they are much better fit by a single simulation model. And if you look at the data across all the kids, we can categorize each child according to the model fit, right? And what that tells us is you see the emergence of these abilities, but what children seem to be doing, and this is, again, a static image of what the kids are doing right now. What we don't have yet is a learning model, and that would be great. But what this tells us is that the children are sampling in some probability from each of these possible hypotheses. And probably what's happening over development is they're sampling with increasing frequency from the correct distribution, right? All the way through the adult representation. Okay, so that's a case where we have some developmental data that is beginning to inform how we might be modeling this kind of development. And again, you'll hear more about it in the poster session. Now I want to talk about another study going much younger on word production and communication. So here we're going to focus on social cognition starting in very early childhood. Because one of the major problems children face growing up is, as we know, they know a lot about the world before language, as you've been hearing. But they, at a certain age, can only say 1 or 2 words at a time. Every child, when they begin to speak, can only say 1 or 2 words. They may have 50 words in their vocabulary, but they're only ever going to be able to produce 1. So given everything they know, how do they decide what to say with the very few words they have? Well, we've thought for decades. We've had a model of what you should choose to say, and the answer is all of our language is limited. You should choose to be as informative as possible. You should choose to say things to people that they don't already know. And we have formal models of this, rational speech act theory, that says, look, speakers should produce utterances that a rational listener will be able to recover the meaning from, and listeners should assume that's what speakers are doing. And consistent with this, we know that speakers do preferentially communicate new information to the listener. And what we wanted to know, was this true early in development, from the very first words? Suppose there are 2 words that are in the child's vocabulary, right? One is known to the listener, one isn't. Do they selectively say the informative thing? So this is the setup.
Look, there's a bear in a room.
The microphone. Good.
Do you see that? There's a bear in a room. Now we're going to ask your grown-up to close their eyes and cover their ears. Okay, now they can't see and hear. Watch what happens next. Do you see that? The bear put on the shoes. Do you see that? The bear put on the shoes. Okay, remember, the bear put on the shoes. Now your parent can open their eyes. What happened? Can you tell your parent what happened?
Okay. And this is the critical moment. What does the child say? Bear or shoes? So again, we designed scenes around words we knew kids knew, and this is a typical response.
What did you see?
That's actually better than a typical response because the child said something. We just can't tell what. Okay, so that is actually what happens here. You lose a ton of data doing this study. We tried to do it a decade ago in the lab. We got exactly nothing. And the only reason we're able to ask questions, experiments on productive language, because there are very few. There are corpus studies, there are checklist studies, very few experiments on productive language in toddlers. Why? Because they don't talk. And so the only way we can do this is online testing at home, where we can get hundreds of kids. Right? And this, I'm going to show you the sample from the first set of data of a couple hundred kids, and we are about to get the results of an online replication with another 200 kids. And I should call out, by the way, my co-author back there, Melissa Klein-Skrull, who originally tried the study heroically in the lab with the kids who didn't talk. But now we're getting the data online. Also, Leah Washington, who's a postback and author of the study. Okay, so here's a child who actually can say full sentences. So she's not useful for our data point because she's going to say everything, but I want to show you what it looks like. It's rare.
Boy! Big! Remember, that's huge!
Shoes?
Okay. Here's a child who only says the informative thing.
Say it again.
S's.
Shoes?
Yeah.
And here's a child who only says the uninformative thing.
What did you see, Jude?
Red.
A bear?
Uh-oh.
Uh-oh.
Okay, so that's the kind of data that we got. And the question is, what did the kids say? And the answer, again, surprised us, right? Because our hypothesis was that they would selectively say the informative things. And in fact, 2 to 1, they said the opposite. They selectively referred to information in common ground. Now, we tilted the design a bit against our going hypothesis, which is that they would say the informative thing. So we're running a replication to see what happens when these conditions are exactly matched. But the really striking thing here is this poses a bit of a challenge to our current RSA models. And it suggests that we need to think about informativity maybe in a broader way, because utterances are only informative at all if the speaker understands them. And for a novice speaker who says things like bah and shoo, right? That may only be comprehensible if that word is already in common ground. And for any of you who have tried to speak in a new language, you know it's much easier to talk about things when your interlocutor knows what you're talking about than if you try to go off book, right? So we are thinking that might happen. We're currently just looking at those models again, and this is thanks to Kartik, who is somewhere also in the audience, looking if rational speech act models can model the difference between a goal of trying to inform versus a goal of trying to be understood or to connect with your hearer. So I'll turn it over to Josh.
Okay, so just to wrap it up here, our ability, this is very early, we've just sketched out these models, but our ability to build models of this kind of communicative language use is going to be key not just to understanding what's going on inside these kids' heads, but really if we want to do the thing that, for example, you heard very clearly from Jacob and Ev there, if we want to be able to understand computationally how kids are able to learn language so quickly, both to understand and to produce from so much less data, we need to understand what their goals are, okay, and the multiple space of goals. And this amazing probabilistic programming language that Kartik Chandra and team built, and it's also part of the Quest platform, is really designed much more generally to capture models of recursive reasoning about reasoning. So theory of mind, or in any kind of communication or cooperation, we want to be able to model how agents form their own thoughts and goals around their representations of the thoughts of goals in others, and so on recursively. And Memo lets you do that in a very expressive probabilistic programming language that has a GPU-accelerated backend building on JAX, the same kind of thing that made neural networks now become this new thing called deep learning, because they work not fundamentally mathematically different than they did in the 1980s, but just thousands or tens of thousands of times faster by using parallel compute. Turns out that's pretty good for computational cognitive science as well. And these are just some of the numbers from the programming language, and again, many university partners are already using Memo. Here, this is just a very simple sketch of a Memo model where basically you can think of the baby's different possible goals. We can see from the data that some babies are being informative. And effectively, here you have a baby who thinks that thinks about the parent representing that they may have some imperfect knowledge of language, and their goal, if you see there where it says what they want, is to inform. They want the parent to be able to basically make a guess about the thing that the parent didn't see. And if you fit that model to the situation, it will predict the thing that we didn't see, which is that the babies are more likely to say shoe than bear. But you can keep the model, but just change the goal. This is the goal to connect or to be understood, and this is just saying, okay, now here the baby wants the parent to be able to guess something that actually is in the scene, so to be able to just understand what they're saying and tie that to just any concept, and you plug that goal in, and then you get the reversal pattern which we saw. So again, this is just very early days. It's just one example of how these new kinds of probabilistic programming languages can unlock the ability to model the multidimensional space of goals that our youngest learners might have. And just to wrap up then the presentation, hopefully you can see how this virtuous cycle, illustrated in a couple of these projects, together with our platforms, both experimental and modeling based, are starting to let us study the whole arc of human cognitive development, from what's built in to all the ways that we start to be able to communicate with other minds, learn language, and then unlock other kinds of thinking with language, as you saw from Jacob in the last mission. And we're far from our North Star, right? But we've been taking the next steps, and together with this amazing team and the other Quest teams, we're really excited to be able to unlock the next steps of this over the next phase of the Quest. Okay. Thank you, and that's it for our mission updates.